Mordecai got my whole story over lunch, so he knows that I actually started at NYU to study tech theater, so I was in Tisch originally. And then I took a Physics 1 class by David Hogg a long, long time ago. And anyway, I decided I wanted to do what that guy did, and now we're here. So you can either blame him or thank him, I guess, depending on how this goes.
And theater is much poorer for him.
Exactly, yes. Think of what they're missing. Anyway, so I thought I would start by sort of setting the context for today, since I'm giving two talks, one talk here and then one talk at NYU. And this is kind of a demonstration of what happens when you write a talk abstract a little bit too far in advance, because since writing my abstract, I actually scoped out a little bit. And so today I thought I would give you really the big picture view of how we're starting to use these objects, these stellar streams, to uncover the history, the evolution of the Milky Way, and to start to map out the dark matter distribution in the Milky Way as well. Tomorrow, on the other hand, I'm going to be much more focused. I'm going to talk about one particular stream, the detailed modeling that we've done of that stream, and what that has taught us about the nature of dark matter. So today is going to be much more of a big picture. This is supposed to be an informal talk, so I thought it could be conversational, and we could have some discussion if you have questions along the way. But before talking about all of that, I want to briefly just mention that there's many other things that I work on as well, and some of them with many of you in the room. So for example, I recently talked about the work that we're doing related to discovering and characterizing binary star systems using the apogee survey. So we're finding large numbers of binary stars using the radial velocity method throughout a huge portion of the Milky Way. We've found some interesting things like compact object companion candidates that are non-interacting, and we're starting to think about how to use those to understand the sort of progenitors to what are now the LIGO events. I also gave a talk in the fall at one of the lunch talks about the work that I'm doing related to galactic accretion, so on some discoveries we've had related to stars that are forming in the Magellanic Stream as the large and small Magellanic Cloud are merging with the Milky Way. But today I'm really going to focus on this sort of third topic about dark matter, about galactic archaeology, and try to give you the big picture view of where I see research going in the next 10 years or so. So I want to focus on this question of how we can use the Milky Way and these words that you may have heard, like galactic archaeology and near-field cosmology, to try to understand and probe fundamental physics. And I think in this context, there's sort of three goals that I think are the core pillars of these two ideas that I want to try to approach. So the first is to map the dark matter distribution around the Milky Way in extreme detail. And so by that, I mean really try to test some of the predictions that have been around in simulations for a long time, like the density profile or the mass profile of the global dark matter distribution around the Milky Way, but also other sort of low-order properties of the dark matter, like the shape or the triaxiality on large scales. By detecting and characterizing dark matter substructure, I really mean trying to find very low-mass things, so substructure that is below the mass of the dwarf galaxies that we see, which if we could find a large population of these things would place constraints on the types of sort of effective models for dark matter that don't produce those things. And then the third thing is how we can use streams to sort of infer or understand the merger history of the Milky Way. And here I'm thinking sort of in discrete events, like the number of mergers per unit time, per unit mass ratio, which is something that evolves with redshift and depends on the mass of the Milky Way and other things. But this is also something that's beginning to be predicted somewhat robustly from large galaxy formation and cosmological simulations. So this is something we can also hope to try to uncover in the Milky Way using all of the stellar kinematic and chemical information that we have for a large number of stars. So we'll go into a bit more detail about each one of these things a bit later, but I really want to talk about how we can make progress on all of these goals using one particular type of tracer that I love, and those are stellar streams. So you saw the moving version of this earlier, but I want to start by talking about what stellar streams are and how they're so useful. So here's a map of the Milky Way halo. So I'm showing here blue things are things that are closer, green things are sort of intermediate distances, red are much farther away. This is some recent work that I've been doing with a grad student at Chicago who was actually visiting here last week, Nora Ship. So there's lots of interesting substructure here. To give you an idea of the demographics of the streams that we know about, and by streams I'm talking about things like the things that I'm tracing out for you in case you're not used to looking at all of these images all the time. To give you an idea of the demographics, there's about 60 streams that we think are candidate disrupted objects around the Milky Way. And about 15 of those are close enough or dense enough that they've been well studied. So they've been followed up. We have spectra, etc. These are just some of my favorites that I've traced out here for you. So you can see there's a number of ones in the southern sky. This is from the Dark Energy Survey. There's fewer, but there's this very prominent one in the northern sky. This is from the pre-imaging for the DESI survey. But all of these objects we think are the remnants of tidally disrupted dwarf galaxies and globular clusters that have fallen into the Milky Way and are now in the process of merging. So there's obviously a number of different ways we can view the sky when we have data for everything. So for example, here's that same map of the Milky Way halo, but now rotated to align with roughly the orbital plane of the most massive stream that we know of. And that's the Sagittarius stream. So that actually connects back to the Sagittarius dwarf galaxy, which is behind the disk right here. So it wasn't covered by these surveys. But this is a large dwarf that's disrupting, and you can trace the tails all the way basically around the entire sky and a little bit farther. There's also, this is now looking at the galactic anticenter, there's also things in this map that aren't actually streams the way that I've defined it, tidally disrupted dwarf galaxies or globular clusters. Especially if you look towards the outer parts of the Milky Way disk. So there's all this blue, which means close structure that looks like feathery features arcing over the outer parts of the disk. These we think are actually tidal perturbations to the outer parts of the Milky Way from the satellite galaxies. But this is actually material that once originated in the disk and has now been kicked 5 to 10 kiloparsecs away from the disk plane. So there's some pretty substantial perturbations to the outer parts of the Milky Way disk. So making maps like this can help us find streams, but also reveal some of this other interesting structure. So I can stare at those visualizations all day, and I do often just look at those visualizations quite a bit. But I want to get back to the goals that I laid out earlier. So the question is, how can streams help with each of these things? So it was realized pretty early on by David and Catherine and many other people that streams nearly trace orbits, and so they provide a lot of information about the underlying mass distribution in the Milky Way. So they can almost directly help us with this question or this goal. They're also extremely kinematically cold. So if you have a passing substructure or a subhalo, the impulse that it imparts on a stream will leave a record in the stream in the density distribution that we can then see later on. So they're one of the only ways that we have to study the really low mass end of the dark matter mass spectrum. They're also, if they're disrupted dwarf galaxies and globular clusters, they're literally just a record of earlier epochs of accretion onto the Milky Way. So you can see how they connect to the sort of merger history of our galaxy. And one of the reasons that they're so informative and so useful is that we think we understand the dynamics of how streams form really precisely. So I'm just showing an n-body simulation here of a globular cluster mass thing orbiting around a very toy Milky Way. So this is looking in the rotating frame, and this is looking in the frame of the Milky Way, essentially. So from an observed stream, like if we stopped this and looked at a bunch of stars here, we can estimate its intrinsic properties, like the age or the mass of the stream. We can, from the track of the stream, we get information about the orbit of the progenitor, which is not something we typically get access to in galactic dynamics. We also have a few examples of streams like Sarah's favorite here, PAL5, that connect back to the progenitor system. So this is Palomar 5, which is kind of the prototypical globular cluster stream, where you can see the tails here connect back to Palomar 5, the cluster. So this helps us sort of calibrate our understanding of how these things form and how different objects disrupt. So interestingly, if you just take the proper motion of the cluster and the distance and the other kinematic properties we have of the cluster, and you just numerically integrate an orbit in a toy model of the Milky Way, and then plot that on the sky here, as we sort of alluded to before, the tails here, the trailing tail and the leading tail, neatly almost delineate what that orbit of the cluster is without ever having to know anything about the cluster or the tails. So now I'm going to focus on each of those goals and go into a bit more detail. I'm going to focus more on this topic, but I'm going to touch on the other two as well, on substructure and the accretion history. So as I alluded to earlier, I think one of the main drivers of galactic dynamics, at least with the capital G here, is to measure the sort of global shape and properties of the Milky Way's dark matter distribution. So is the density profile NFW? Are the outskirts, like beyond a tenth of the virial radius, are the outskirts of the Milky Way's halo triaxial, or is it more spherical? So these are kind of second order predictions from simulations, but they're things that we can actually check in the Milky Way, and so we should do that. The obvious challenge here is that we want to measure something like the density of dark matter on large scales, but we don't actually observe the dark matter, hence its name. We observe, the luminous things, the stars, the gas, etc. So then, from these surveys like Apogee and Gaia and etc., we do have access to kinematic information like the position and the velocity for a large number of stars. And especially over the next few years, we'll have that information for hundreds of millions of stars, so a pretty big sample. This doesn't immediately tell us the dark matter density, but these stars are orbiting in the acceleration field that's sourced by the density. So if we can use the kinematics here to learn the acceleration field, that is enough to get us back to the density, and then we're all happy. Now the challenge here, though, is that at best what we have is something like the instantaneous tracer phase-space distribution function. That's a very fancy way of just saying we have positions and velocities of stars today, and today only. We just have a kinematic snapshot of the Milky Way. And we want to use that to learn about this acceleration field. So there's actually no necessary connection between these two things. We could just be observing the Milky Way at a really special time when all of the stars happen to be configured in the state that they're in now. And if we looked again in a billion years, they would just fly apart again. We wouldn't be able to do any inference, right? So one solution to this problem is to use something like genes modeling, where you make very strong assumptions about the Milky Way, like the symmetry properties or the equilibrium state. And you may painfully remember many chapters in Binney and Tremaine devoted to this topic. But we know that actually all of the assumptions that we use to go into methods like this are violated in the Milky Way. We know that we don't know actually what the symmetry properties of the Milky Way are. We see signatures of disequilibrium that I'll talk about later. And so these types of assumptions will then bias the inferences that we make. Now, the problem would be a lot easier if instead of instantaneous phase-space positions, we had actual full orbits for stars, or even segments of orbits. Because if we had orbit segments, we could actually directly measure the acceleration. If you have an orbital trajectory, you know the acceleration local to that orbit. And that, for example, is how Newton determined that the force law of the solar system falls off like 1/r². He saw that the orbits of the planets are closed ellipses that connect back on themselves. It would be a lot harder if you just had the positions and velocities for all the planets at one instant in time and then had to try to learn about what the solar force field is. So if we had orbits or orbit segments, this would require many fewer assumptions. So then the question is, how do we see orbits? And that's where streams re-enter the picture. So as I mentioned before, from a single snapshot of the kinematics of a stream, we get information about the orbit that the progenitor system is on. But there's actually quite a bit more information in a stream, and that's because the stars in a stream are all on different orbits that are slight deviations away from the orbit of the progenitor system. So what that means is if we observed a bunch of stars in a stream today and we got their positions and velocities, if we integrated their orbits backwards in time in a bunch of trial different distributions of mass, if we got that distribution correct, like if we got the model of the Milky Way correct, all of those small deviated orbits should vacuum back into the progenitor system. So I'm looking at these simulations in the rotating frame, so things look a little crazy. But here in the correct model for the Milky Way, they suck back into the progenitor, and over here, crazy things happen. Yeah?
And that's robust to numerical issues? Like,
what do you mean by numerical issues?
Well, the gravitational systems are chaotic, right? So if you get your starting snapshot slightly wrong and run it backwards, you don't
Agreed.
End up at
We're in toy world right now.
Okay.
Yes. So this is a cute idea, and so we use this sticking in the toy assumption. I'll come back to exactly that point though later on. Sticking in this toy model of the Milky Way that we're thinking about, it's even not that nice because we never actually observe the positions and velocities of stars infinitely precisely. There's always finite observational errors on the quantities. And something weird happens because we actually observe a heliocentric spherical transformation of the true positions and the velocities of the stars that also involves the motion of the sun around the Milky Way. So things are a bit more complex. We often also have missing dimensions here, so it's not like we can just take all of the stars that we see in a stream and numerically integrate their orbits backwards, because we often don't have a distance or have a very poorly constrained distance. But that's totally fine from the perspective of a generative model. So if we knew the true position and the velocity of a star, and we knew the solar motion and position, we could evaluate the likelihood, because we have good likelihood information from surveys like Gaia and Apogee, and et cetera. So we could just absorb the position and the velocity of every star in a stream into our probabilistic model as latent variables that we also need to infer along with the rest of the properties I care about, like the acceleration field sourced by the dark matter, the progenitor orbit, but also things like the mass loss history of the progenitor. So if we knew the orbit of the progenitor system, and we knew the time that each star in a stream was stripped out of the progenitor, then basically we can get their true position and velocity today just by evolving them under this acceleration field, and that gives us a clear path to being able to evaluate this likelihood. So generically, you have to model all of these different things that are in the white background circles all together. So that's a lot of parameters to cope with. This model has a few nice properties. I think the most promising aspect of it is that you can put anything you want into this acceleration field. So it doesn't just have to be a toy model for the Milky Way, although I'm going to demonstrate a test using a toy model of the Milky Way. But this could be something complex and time evolving even if we wanted to, and we'll see later on why that's going to be important. But one of the not so nice properties of this model is all of these latent parameters that are in the model. So because we don't, we need to be able to map from the true position and velocity to the data that we have today, we need to add in the 3D position and the 3D velocity for each star into the model, along with the time that it's stripped, which connects back to the mass loss history. So computationally, this is a little bit of a challenge. But we've tested this on some simulations that we've run of the Sagittarius stream. So that this is the final snapshot of an n-body simulation of Sagittarius that I'm showing here. Just to test the waters on doing this kind of inference to see how precisely we can measure the parameters of the model that we use to run the simulation. So we run the simulation, we then mock observe some stars, assuming Gaia-like proper motion uncertainties, and that we can measure their distances. And we assume that we also have some independent measurements of the progenitor system today. So we know the position and the velocity of the progenitor system because we need to integrate the orbit of this thing along with the orbits of the stars that are actually in the stream. So then once we have those mock observations, we can run the model that I showed you before and try to see if we recover what we used to run the simulation. One caveat here is that I put 4 crosses here because we did this with very few numbers of stars. And the reason is exactly that factor of 7, the number of latent parameters that we have to cope with when we're trying to do this kind of inference. So the number of parameters scales like 7 times the number of stars that we want to use in order to learn the properties of the dark matter. So we just stuck with n equals 4, which is already a lot of parameters here. But still, the results from doing this kind of test are pretty promising. So just 4 stars in a stream that we measure with Gaia-like uncertainties, and we have good distances too. We can recover the input circular velocity of the halo and something about the shape as well. So here we ran this in a prolate dark matter distribution, so we can recover that using just these 4 stars. Now that was 4 stars. Typically we have hundreds of stars, or at least tens of stars in the stream. So extending this to real data is going to be, but it at least has pretty promising constraining power, given that this is just using 4 stars, right? Okay, so now getting back to Sigurd's point, which is that was all kind of a joke in a way, because it was all done in an extremely naive representation of the Milky Way, where it's a static, time-independent galaxy. It's a fixed mass profile, dark matter distribution, etc.
Did you just call the entire field of classical dynamics a joke?
Yes.
Yes. So.
No, I called what I did a joke, which maybe you shouldn't do in a job talk, but whatever. The reason it's a joke, though, is that now we know the Milky Way is extremely dynamic, essentially on all scales. So in the disk, for example, you can look at the vertical kinematics of the stars in the really local solar neighborhood, and this is something that Sarora Gandhi, who's a grad student at NYU, is working on, actually, with a group of us here. And you can see unmixed perturbations from satellite galaxies, just in the local velocity distribution around the sun. So even at 8 kiloparsecs into the disk, we see perturbations from satellites mostly. So this immediately will bias what you may have learned as the Oort problem, trying to determine the dark matter density local to the sun using these vertical kinematics. But as I showed you before, we also see these distortions in the very outer parts of the disk. So it's not just near the sun, it's very far out into the disk as well, almost into the halo. So if you're perturbing the outer parts of the disk 5 or 10 kiloparsecs away from the disk midplane, that's no longer a disk. That's some crazy, wobbly thing in the outer parts of the Milky Way disk. So this will immediately make determining the rotation curve out beyond 12 or 15 kiloparsecs much more difficult and kind of meaningless in a way. So the inner Milky Way, and here inner, I mean where the disk is. The inner Milky Way is very dynamic, and so that already suggests that the toy picture of the Milky Way that I showed you before, static, simple mass profile, that's kind of out the window. That was all for the disk. What about in the halo? We also actually see pretty strong evidence for time dependence and disequilibrium far out into the Milky Way's halo. And I think the strongest case for that comes from this blip right here, which is called the orphan stream, which was discovered in the Sloan Digital Sky Survey, so about 15 years ago or so. We think it's the remnant of a dwarf galaxy that's now, we just see the stream that's left over. It's pretty massive, so I think the original stellar mass of this thing had to be about 10 to the 7 solar masses or so. And it's called orphan because there's no known progenitor system for it. It looks like it's just the stream that's left over. So once Gaia DR2 came out, so the original part of the stream was only traced to the bottom of the northern footprint here. Once Gaia DR2 came out, we searched for more stars that could be members of the stream. And we found these RR Lyrae type pulsating variable stars that are typical to dwarf galaxy, old metal core stellar populations. We found these RR Lyrae in the stream that essentially extend the stream pretty far into the southern hemisphere and almost wrap around the whole sky. These horizontal branch stars are nice because they're essentially standard candles. They're like Cepheids. They pulse with a predictable period that scales with the luminosity. And so we get very accurate distances to all of these individual stars in the stream. So you can make images like this where you instead transform the sky position and distance to each star in the stream into Cartesian coordinates, and you don't see that the stream just blows up entirely. That's because the distance precision is so good to these individual stars that you can essentially resolve the thickness of the stream. So the key thing that we found with Orphan, this was the known part of the Orphan stream up here. We extended it quite far into the southern part of the galactic hemisphere. And we found that the stream is actually about 100 kiloparsecs in length. So you can go to this visualization here if you have your laptop out and see an interactive version of this. But the point is that the stream is now essentially going through the disk all the way out into the galactic halo, both in the southern galactic hemisphere and the northern galactic hemisphere. So that'll be important in a second. So we can take the same RR Lyrae stars that we now know are part of the stream, and we can start to look at their kinematics. So now instead of looking in Cartesian coordinates, I'm back to spherical coordinates, but in a coordinate system that's roughly aligned with the elongation direction of the stream. So this is like longitude along the stream and then latitude away from it. For a typical stream, the proper motions or the velocities of the stars in the stream on average point along the stream. So we expected that once we looked at the proper motions of these stars, they should point in this direction uniformly across the whole part of the stream. Now I'm plotting the proper motion vectors here of little segments of the stream, so averaging over small angular subsections of the stream. Interestingly, there's this deviation here towards the center. So this is at the point where it's closest to us right now, and then over here the proper motions point along the stream again. So it looks like some kind of external perturbation gave these stars in the middle part of the stream some extra velocity perpendicular to the stream. And this won't survive for very long. So if you wait another orbit around the galaxy, the stream will no longer look like a stream because you need to be elongating in the direction of the stream in order to stay coherent. So one question then is what could have caused this perturbation? Well, it turns out the Orphan stream is so long that it actually intersects the orbital plane of the Large Magellanic Cloud. The Large Magellanic Cloud is this very massive dwarf galaxy pair, actually, the Large and Small Magellanic Clouds, that are on their first infall into the Milky Way. And we think that actually the LMC had a direct effect on the stream and caused this velocity offset in the center part.
Adrian, can you point out where that offset is in the figure with the LMC on it?
Oh, with the LMC.
Sorry, I couldn't quite.
I can't.
I don't think you said. Said Siri.
Hey Siri. It's this part here.
Okay, cool.
Yeah, so it's actually just a little bit beyond. If you trace their orbits backwards, this is the part that was closest to the LMC in the past, and now they're slightly forward again. So if you then try to model the track of the stars that we see and sky position and proper motion, and we even have some radial velocities for some of these stars, the only way you can explain the deviation in the track of proper motions and some strangeness in the sky positions is if you include a very massive LMC. typical to the masses that other people are finding now, that it's basically comparable to the enclosed mass of the Milky Way at the radius that it's at right now in the Milky Way halo. So while I showed that streams can in principle deliver very precise constraints on the dark matter distribution, at least in the context of the toy models that I showed before, that was all a joke in the sense that we know things are much more complex. We see time dependence in the inner parts of the galaxy. We see perturbations from satellites in the outer part of the galaxy. So if we want to try to actually make progress on this, we really need to face up to including time dependence and non-equilibrium structures into the modeling that we're doing. So in the past, modeling streams, a lot of people kind of fit these toy models. Like you can go to chapter 3 in Binney and Tremaine and read out different potential models. They try to fit those to the Milky Way and hope that those were telling us actually robust measures of the summary properties that we want to measure, like the mass profile and the flattening. But I think the way we're going to go forward is to instead fit these toy models so we can get out those simple numbers, but with flexible deviations that allow us to absorb and simultaneously constrain the complexity around those models. So that's a very vague statement, and I said that like there's an obvious path for what to do there, but there actually hasn't been very much work on doing this in the modeling perspective. So I've been thinking about one possible path that I think is a really nice connection between the galaxy formation group here, the dynamics group, and the data group. So I'm going to just lay out that plan, and it's something that we can discuss later if people are interested. So first, we have pretty good models now for how dark matter halos grow and evolve. So we have cosmological simulations, and we have a lot of them. And those essentially predict the typical growth histories and time dependence that we expect to see in dark matter halos like the Milky Way. So we should be able to use all of these simulations that we have to somehow extract a compressed representation of this kind of evolution, both spatially and in time. So for a Milky Way mass halo, I should be able to say, what's the typical spatial and time evolution of the dark matter halo? So I'm imagining something like a basis function expansion that you would do for the density field, but now where you've also included time as another dimension that you're expanding around. And that's sort of new mathematical territory, but it's something that Martin Weinberg's group, for example, has made some initial promising progress on. So anyway, if we're able to extract these kind of compressed representations and very quickly evaluate the state from these representations, we'd then be able to simultaneously just put these in with the toy models that we're trying to fit using something like the stream rewinding that I was showing before, and get constraints simultaneously on this complex time evolution and on the summary properties. So I think there's a lot of great student and postdoc projects sort of in this space that make really good connections between the different groups here. So that was all about the sort of first goal that I mentioned before, which is just mapping the dark matter distribution really globally. But now I want to just briefly mention the other two as well. So the second goal that I mentioned was detecting dark matter substructure using stellar streams. So it was also realized pretty early on that not only do streams give you orbital information about orbits around the Milky Way, which is useful for constraining the sort of global distribution of dark matter, they're also extremely useful as tools for studying small-scale substructure as well. And as I mentioned before, that's because they're very kinematically cold. So they have velocity dispersions that are typically less than a kilometer per second. So if you have a passing subhalo that imparts a velocity kick on a small part of the stream that's of order a kilometer per second or larger, that will then imprint on the density evolution of the stream. So here's a sort of gallery of simulations of streams that have been perturbed by different configurations of subhalos with a mass range from about 10 to the 5 to 10 to the 9 solar masses or so, just to show you the kinds of things that can happen to a stream evolved under lambda CDM predicted dark matter only universe. So this is very interesting because at these low masses, which have a direct effect on the evolution of streams, we don't have many other ways of studying the mass function down here. And as I mentioned before, this is really interesting because this is where you start to see deviations between cold dark matter and other dark matter theories like fuzzy dark matter, warm dark matter, and et cetera. So I think this mass range 10 to the 6 to 10 to the 8 solar masses or so is going to be one of the most interesting ways we can use streams to try to constrain these effective models for dark matter. Now, what are the complications here? So tomorrow I'm going to talk about that in a lot more gory detail. Today I just want to flash a couple things that might be sticks in the side of that story. things that also can affect the density evolution of streams. So for example, with Sarah, we worked on what the galactic bar, the time-dependent galactic bar at the center of the Milky Way, what that can do to streams as they orbit through the disk and come close to the center of the galaxy. So with Pal5, for example, this is the stream I showed you before. Here's the cluster. This is the trailing tail. This is the leading tail. We knew something funny was going on with this stream, because if you just look at the leading tail and compare it to the trailing tail, it's about half as long, and it's about half of the density of the densest part of the trailing part of the stream. And if you just run a simulation, an n-body simulation of a disrupting globular cluster like Palomar 5, you don't generically get these kinds of asymmetries if you use a very toy model for the Milky Way, like a static, time-independent model. So we then sort of repeated those simulations, but just included one extra component, which is a time-dependent, rotating galactic bar model. And if you do that, these types of asymmetries are a natural outcome of that kind of simulation. Essentially because different parts of the stream, as the stream is passing through the galactic disk, will see the bar at different phase angles. And that imparts a different torque then on different parts of the stream. So that can have the same effect that a large subhalo would have on a stream, in that it can cause a velocity kick to stars that makes them then later on evolve in their density. So we think that these kinds of asymmetries that we're seeing in Pal5 can actually be explained from perturbations from the galactic bar. But there's other more boring or baryonic effects that can also imprint themselves on streams. So theoretically, this has not been observed yet, but theoretically, giant molecular clouds can also have an impact on streams. So if you, again, with Pal5, which is passing through the midplane of the disk at about 7 kiloparsecs or so radially from the center of the galaxy, there's a lot of substructure there in the distribution of gas in the Milky Way's disk. Those can actually do the same thing that subhalos do. The one difference is that they're slightly lower density, so they don't have as dramatic of an effect, but they can still cause density perturbations along the streams. Another thing that can happen is what I showed you before with Orphan. So you can have other large satellite galaxies of the Milky Way that come close to some of the streams and leave more large-scale distortions to the streams that may evolve into more complex morphologies later on. So that was with Orphan and the LMC, but we actually think that, and this is some new work that I've been working on, Pal5 actually comes pretty close to the Sagittarius galaxy itself. So we think that this might also be a contributor to the funky morphology that we see for Pal5. So Pal5 has really had a rough life. It's actually really surprising that it's such a neat, coherent thing today. It makes you wonder what's hiding behind all of this noise, whether there's lots of perturbed substructure away from the stream. So while streams are a very promising avenue for trying to constrain the low mass end of the dark matter subhalo population, we're beginning to see that there's many other complex processes in a real galaxy that can actually also imprint on the density evolution of these streams. So I think we need to do much more realistic simulations beyond just inserting a rotating galactic bar model into a static time-independent Milky Way, in order to really understand how much these things matter and on what scales, so that if we see density variations in a stream, we can uniquely map that back to constraints on dark matter. Okay, finally, the last thing I want to touch on is how we can try to study the accretion history or the merger history of the Milky Way. So again, this is in the context of thinking about individual merger events with the Milky Way as a function of time, for example, which is a thing that you can extract from some of these large galaxy formation simulations. So if we want to measure the merger rate in the Milky Way, one obvious thing to do is to just look at all the dwarf galaxies that we have and try to reconstruct what their orbits are, and then see when they fell in, and then maybe that will tell you the merger rate. But many of these satellites are not actually disrupting at all yet. They don't show any signs of tidal debris or extra-tidal debris. So if they are tracing the merger history, they're really just tracing the tail of the orbit infall distribution of things that don't disrupt. So it's related to the merger history, but it's not a direct trace back to that. On the other end of the spectrum, instead of looking at the bound things, you could instead try digging around in the trash heap that is the stellar halo. And that's something that people have been really starting to do within the last 2 years or so, using primarily data from the Gaia mission, and again, these large spectroscopic surveys like Apogee, which give us chemical information. So the emerging picture from studying the bulk distribution of the stellar halo around the Milky Way is that we now think that most of the stellar halo was contributed by very few sort of 1 to 10-ish mergers very long time ago. So by total mass, we think most of the stellar halo is just from 1 or 2 large mergers a very long time ago. But by number, if we want to try to reconstruct the dn dt d mu, by number we expect many more smaller mergers over that same amount of time. And the question is, how can we pick those out over the bulk of the mass, which was contributed by very few mergers? So we're starting to be able to do this by combining both dynamics and chemistry. So for example, if you look in the space of energy and angular momentum for a bunch of stars, and you also cluster on chemical properties like the metallicities of stars, you can start to pick out other smaller merger events. So this was from a paper by Helmer Koppelman last year, where we identified 2 more clusters essentially by combining dynamics and their chemical properties. And they're called Thamnos 1 and 2. Anyway, there's not a lot of good names for the things that we know of that formed the Milky Way halo. In any case, these 2 things, satellite galaxies and the bulk, like smooth stellar halo, they clearly contain a lot of information about this quantity, the accretion rate onto the Milky Way as a function of time. The stellar streams, though, are really the missing connection between these 2 things, because they're the future state of the satellite galaxies that we see that are bound today, and they're sort of the less mixed versions of the things that have merged with the Milky Way a long time ago and are now much smoother and distributed throughout the whole stellar halo. So how can we use the stellar streams in order to try to combine all of these things to measure this quantity? To make this connection, there's a few key ingredients that we need. So we need models for the infall rate, the infall orbits, and the mass function for all of the things that we know are merging with the Milky Way. And we have models of those from cosmological simulations, so people have been able to extract these types of distributions from galaxy formation simulations. On the observational side, we also need to be able to measure our survey selection function. So we need to be able to say, in a given part of the sky, how deep can we see, and would we be able to see a stream if it were there? So this type of thing, the survey selection function, which is really just based on how deep you can go, what's your photon noise limit essentially in a given part of the sky. These 2 things we have a pretty good handle on how to do right now. But there's sort of 2 missing ingredients here. And the first one on the theory side is we need to be able to predict the density evolution and the morphology evolution of streams so we know when they fall out of our threshold of detectability. And we can do this in sort of, again, toy models for the Milky Way, where we know that roughly the density of a stream will fall off like a power law with time, usually like time to the 3rd power. But we don't know how to do this in the presence of all of the other complex things that are going on in the Milky Way, like the subhalos, like the bar, giant molecular clouds, etc. So we need to be able to develop this kind of robust simulation of stream densities in order to invert the population of streams into an accretion rate. My voice is losing, it's going away. The last thing on the observational side, so the selection function tells us, could we see a stream in a given part of the sky? But there's another piece of the puzzle, which is, did we see a stream in a part of the sky? And what's the detection efficiency of finding a given stream like that in that part of the sky? And the challenge here is that we don't actually have any really robust automated stream finding methods. So if you wanted to actually estimate this quantity right now, you'd have to put probes into very few people's brains. I'm totally losing my voice now. You'd have to put probes into a few people's brains and try to model their pattern recognition cortexes in order to see whether they find a stream or not, given a part of the sky. So again, we're at this crossroads where streams clearly encode information about the destruction rate of satellites, about the merger history of the galaxy, and they really provide this link between satellites and the diffuse stellar halo that we were able to study now with Gaia. But if we want to use the streams that we see in order to infer this thing, to do this inversion, we're missing these 2 key pieces. Models of stream density evolution in more realistic environments, and the survey detection efficiency. I actually have water up here. I just haven't been drinking it. Thank you, Drummond.
I'm drinking myself.
I might need it in a second. These things, you're talking all day, and then you're supposed to give a talk at the end of the day. It's crazy. Anyway, so I put in a pre-doc project specifically thinking about Nora Ship, who I was working on the maps of the stellar halo with before, because I think we can actually make progress on both of these things simultaneously. So there's lots of other opportunities here, but I'm really interested in pushing on survey detection efficiency and automated stream finding, and on making these more robust models of stream evolution. So in the last few minutes that I have, I want to briefly mention what I see as sort of the future of stellar streams research, and at least as they connect back to the goals that I initially laid out. So if we go back to those goals, so we want to map the dark matter distribution in detail, we want to detect and find dark matter subhalos around the Milky Way, and we want to be able to infer the accretion history of our galaxy. One of the things that we've learned is that things are a lot more complex than we thought, sort of 10 or 20 years ago. So for example, there's eminent time dependence and disequilibrium throughout the galaxy, both in the disk and out into the stellar halo. In the context of detecting subhalos, we think that the densities of streams, or the density evolution of streams, is really contaminated if you want to try to find dark matter substructure by different galactic dynamical phenomena, like the galactic bar and other baryonic things. And finally, if you want to try to measure the galactic accretion history, we need to be able to simulate how streams evolve in much more realistic, dynamic environments, rather than the simple toy models for galaxies that we've been using for a long time. So in the next decade, I think we'll be able to deliver on a lot of these things, even in spite of this. So I think sort of in the next 5 to 10 years, we will see more robust determinations of the Milky Way's mass profile, of the shape, and sort of first constraints on the time evolution and the growth of the Milky Way's halo. We'll also start to see constraints on dark matter models, more effective dark matter models, I would say, like cold dark matter, warm dark matter, basically by detecting or placing limits on the very smallest mass end of the dark matter subhalo mass function. And I think we'll be able to do the first stream population or accretion history inferences by pushing on automated stream detection so we can measure our detection efficiency, and by improving the simulations we have. The reason I think we're going to be able to do this is because we know what's required in order to be able to do this. So we know the pieces that we're missing in order to make the measurements of the Milky Way's mass more robust. We know that the different things that can, in principle, perturb the density evolution of streams, so we need to model those better, simulate those better, and essentially be able to connect the density structures that we see back to the dark matter models that produce subhalos that can perturb the streams. And then finally, we know that we need to somehow determine our detection efficiencies from surveys, whether that involves doing surgery on people and modeling their brains, or whether we can actually do this more automatically using simulation or using machine learning. That's an open question. So the key points I want to drive home here are that stellar streams provide a really clear path towards precisely constraining the distribution and the nature of dark matter around the Milky Way. However, over the last 10 years or so, we found that in all regards, things are much more complicated than we originally thought. However, I see that as an opportunity, because that means with careful modeling, we can study interesting dynamics, we can study the evolution of the galaxy, and we can place constraints on fundamental physics like dark matter. So I'll end there, and hopefully I won't have to talk again.
We'll turn on the...
Oh, yeah.
Yeah, here we go.
Uh-oh.
That was not...
Now I need Drummond's water. He took it away.
Yeah. Okay, any questions, Sarah, and then we'll go to the back?
Yeah, I was just curious, so compared to other mass estimates of the Milky Way, say from the globular clusters, did you ever try just for fun to see how your rewinder would do with Gaia errors for a few stars in Sagittarius? And if yes, was it different? Because those should also be biased against the fact that they're not taking into account the time evolution, right? All of
Are you asking, did I try it with data for Sagittarius, or did I try it with...
Yes.
Oh, yeah. I haven't done it with Sagittarius. I did try with Palomar 5. The challenge I immediately ran into is even at the precision that we have for distances to individual Aurora Lyrae in PAL 5, it's still not good enough to be able to rewind in very precisely. Like it quickly makes the likelihood very challenging to compute, and so I haven't actually done that. But in principle, as I was talking to Shirley earlier, it should be doable. It just might take a lot of time.
You want to just choose questions?
Sure.
So I'm not sure if this question makes sense, but in the beginning you said that there are like 60 known streams.
Yeah.
And for measuring these more like global properties that you were talking about in the beginning of your talk, how many streams would you like preferably like to have in order to get these things down to a level of error that?
Yeah, that is a great question. So one person who's tried to tackle that is Anna Bonazza, who looked at, again, in the context of very toy models of the Milky Way, how different pairs of streams that we see contribute to like improving the likelihood on different parameters that we have. But that was all in the context of we know the mass distribution, the model for the mass distribution, we just want to know the parameters. So you can do that kind of forecasting. It's kind of analogous to forecasting for CMB missions. But personally, I don't think like that intuition won't map onto trying to understand the more complex things, like the time evolution and the dynamic parts of the Milky Way. So I think what she found, though, is if you pick the right 4 streams, you can get sub% constraints on parameters like the mass. But that's, again, with all those caveats.
Okay, Shirley, then Shirley. Or did you?
What about me?
Rachel was up before. Raise her hand again. Sorry, Rachel, then Shirley.
So this is really cool, really beautiful work. Thanks for a nice talk. I've heard, though, that there are other galaxies besides the Milky Way. So I was just wondering, in the context of thinking about upcoming new telescopes where we might be able to do resolved stellar population studies in other galaxies, what are the prospects for studying some of these things like the merger history, the stellar halos, how diverse they are from galaxy to galaxy, some of those issues. I realize you won't have nearly as precise information, especially on the velocities, but have you thought about that at all?
Yeah, so I think there's 2 angles. One is the question of what can you learn just from the projected morphologies of streams.
Yeah.
And some people have started to work on that. Sarah is interested in this, I know, as well. But it is an open question. The question is, how many dimensions do you need, phase-space dimensions do you need in order to measure something like the flattening of a halo? So if you're interested in...
And you might be able to get metallicities, right?
Fair enough, yeah. So I think on one side, it's unclear what kind of dynamical information just having a projected map of a stream gives you. On the other hand, if you are able to get metallicities and a radial velocity and other things, can you still reconstruct the merger history, the accretion history, without being able to reconstruct the mass or something like that? And I think that there is a lot of promising work being done on that by David Hendel and other people, thinking in the context especially of W first.
Okay, thanks.
Sure.
So you're mentioning why these compressed dark matter halo cell representation have been more realistic. So if you were going to make a wish list of how you get these compressed representation, other than just run the whole simulation through, right? What would you want? The second sort of related question is like, what kind of stream features do you expect when you have these like weird dark matter candidates?
Weird dark matter candidates.
They're not cold dark matter.
Okay, yeah. So let's start with your first one. Did you have a slide in mind? Ah, perfect. Thank you. Now I'm thinking about your second question, so I've forgotten your first one. Let's start with your second question. So one of the interesting things is that, and this is something I'll talk about tomorrow with everybody at NYU, there's kind of a disconnect right now between the way astronomers and people who are studying the halo, the way we're thinking about constraining dark matter and the way the particle physicists are thinking about it. So really, I can only speak to the sort of effective models of dark matter for which I can simulate some aspect of it, like cold dark matter, warm dark matter. Now people are actually doing this for fuzzy dark matter, et cetera. And there, I think I've even abstracted one step beyond that to say we don't need to actually be able to simulate a stream in those different models for dark matter right now, but we can just try to constrain the bulk properties of the subhalos that we see, and then ask, can a given dark matter model produce a subhalo like that? So I think that's one possible avenue, is to take a more agnostic approach and see what we can learn, and then see how that imprints on the effective models that we have for dark matter. What was your first question now?
The first question was, you were mentioning these compressed dark matter
yes.
halo representations.
Yes.
What do you want with
Yeah.
compressed representations?
Good, yeah. So what I want is like a subset of the particles from dark matter simulations at a bunch of different time steps. And to zeroth order, the thing I could imagine doing is constructing a basis function expansion representation, like a low order expansion of the density distribution, and then try to somehow connect the expansion coefficients over the different snapshots that you have. Because the evolution of those different expansion coefficients at the low order end will tell us about the bulk, large scale evolution and changes to the dark matter halo. So that's specifically what I want from people who have access to simulations. I'm looking at a few people right now. But it's a new direction. It's something that I don't know what to do if I were to sit down at my laptop right now and work on it.
So you showed these examples where you had some streams and there was an anomaly in the velocities and you found an object that matched that, the LMC. Do you have any examples of other anomalies that don't have a known object causing it? I guess you would have said so if you had it, but...
Well, actually we do. Yeah, I don't think I put in images of them. Yeah, so there's a few, okay, wait, no, I can. This is gonna require you to put on your astronomer goggles though. It's gonna require some squinting. So, believe me when I say that right here, there's a sort of bluish hue. Do you see a bluish hue right here? Okay, good, all right. There's a stream there called Jhelum. It's named after a river in India. And Jhelum is really weird because it looks like it's a thin stream. You can actually see there's kind of a ridge line here. But if you use it's close enough that we have Gaia data for the stream. And if you make a filtered map of the stream, it has a thin component and then a really bizarre wide component around it as well. But it has a total mass that's typical of a globular cluster. So we have no explanation for that. It could be something very, very complex, or it could be maybe the globular cluster was inside of a dwarf galaxy and they both merged, and now we're seeing a really complex distribution of stars, but we don't know. But there's other streams like that where we don't have an explanation. Actually, sorry, one of the most famous examples is this one, Sagittarius, which is it's the stream that you find when you're trying to find other streams. You accidentally find Sagittarius. And the reason it's unexplained right now is there's this bright component that you can trace here, and then almost parallel to that, there's a fainter component that runs above the bright part of the stream. And so there's a lot of different things you could come up with to try to explain this, like maybe it was rotation in the dwarf. Problem is we don't see rotation in the thing that's left over, and we don't see lots of signatures of rotation in the tails. Maybe it was two dwarf galaxies that fell in together, and one of them disrupted and formed this stream, and the other disrupted and formed that stream.
Sometimes something wrapping all the way around, and you see it twice that way? Or?
No, because these are at the same distance. So it's very strange. So I think Sagittarius, which is the thing that you can't not find, is one of the most unexplained streams. Sorry to interrupt you.
So if you were to, this gets into the program of figuring out what came in and how long did it survive. If you look at the fraction of stars in streams
Yes.
that have identified in streams as a function of galactocentric radius, what does that look like?
I have not made that because that plot. I expect the selection function to really
No,
imprint
the
on
selection function is a big effect on it.
Yeah.
But my sense is that the fraction's the fraction ought to be much higher at large galactic centric radius.
Right. Yes.
Because the disruption mechanisms are important at small galactic centric radius. And I think you could probably write down something almost like a continuity equation if you assume that we're not at a very special moment. And imagine when the clouds are coming in, there's something special.
Yeah.
But that since things are going to be coming in, they're going to be destroyed as they come in, that even without knowing the destruction mechanisms, the radial dependence, once you deconvolve the observational selections, which I think are not trivial, but are not trivial, might give you a handle on this.
That's fair. You still though need to know something about how the densities of streams evolve with time, like how they fade out of your selection in a sense, right? So if the dominant things that are causing streams to diffuse are different at small galactocentric radii versus large, you need to be able to resolve that, right?
Yeah, but I think you could model the radial dependence
Yeah,
of the
of the
effects
diffusion.
better than you know they're.
I see what you're saying. Yeah, that's fair. Yeah, that's an interesting idea.
Very nice. So I guess baryonic effects can change things for thermal substructure.
Wait, say the first word.
So baryonic thinking.
Oh, yes,
baryonic
yeah.
effects, and if you are in your idea of this halo model, if you're thinking or do you mind incorporating baryonic effects in some way?
In the halo?
I mean, when you were referring to using cosmological simulations,
Oh, yeah.
like thermal halo registries to build your effective model, then do you mind also incorporating feedback like baryonic effects?
Well, yes, but I would rather do that after you simulate it. So I'm happy to take different simulations that have different prescriptions and then see what those different things then lead to down the pipeline. But I don't think we need to include feedback as a tunable thing in our simulations of streams, if you know what I mean.
Yeah, but I guess you could build similar models out of like a bunch of different simulations.
Yeah, I see what you're saying.
Have
Yes,
different
yes,
feedback.
absolutely, yeah.
Any other questions? Okay. Thank you again.
Oh, sorry.